The simulation tool that is built into the analysis software is one of the most powerful features of the software and unique to race technology. Whilst timeslip is very useful, it is only a comparative tool. It tells you how much faster or slower you are going compared with your best performance, and is great for building consistency. But what it can't tell you is whether it is possible to go even faster. That is exactly what the simulation tool is for. Think of it as like lending your car to the very best racing driver and letting him set a couple of qualifying laps. Then use this information to highlight areas that you can make the greatest improvements. In this example, we will set up the simulation tool as simply as possible to highlight an area where the car can be driven closer to its limits. Before we start, we need to check that we've got a minimum of sim speed, sim timeslip, and sim timeslip rate enabled on the variable manager. Add a lap marker as normal. To keep it simple, we will just use a lap marker. If we look at the lap and sectors table, at the top we can see that under the theoretical and best continuous lap, we have the simulated lap time and sim delta. If the simulation is not set up correctly, these numbers are meaningless. Before using the simulation, it needs to be configured so it knows something about your car. Setting up the car's details for an accurate simulation can be quite time consuming. However, it only needs to be done once, and it can be kept until you make significant changes to the car. The simulation tool works on calculations based on three factors: braking forces, cornering forces, and accelerations. To get the maximum braking force, we can either look at some data from the car, or make a guess. Looking at the data, we can see that the maximum braking force for the lap was close to 1.05 G. For road tyres, the top limit would typically be 0.9 G, a performance track tyre 1.1 G, and for slicks this can increase to about 1.3 G. If the car has aerodynamic aids like large splitters or wings, then the grip will be higher than this at speed, as the car is pushed down onto the track. In this scenario, it's best to enter the grip level that is speed dependent. For example, a car that has slicks and large wings, at low speed the grip will be about 1.3 G, but could be up to 2 G at 160 km per hour. The setup for both braking and cornering is identical, and for most applications the same grip will be used for braking and cornering. Setting up the simulation for acceleration characteristics is more complicated, and there are a few options. The information entered is used to calculate the acceleration characteristics of the vehicle, either acceleration as a function of speed, a simple power figure for the car, or a power curve. With the power curve, it is also possible to input gear ratios, which is a fantastic tool for testing ratio changes to see the effects on the lap times. We will use the simplest, the single power figure. The power is required in kilowatts, and this is the power available at the wheels, not the engine power. You also need to know the vehicle weight on track with fuel and driver weight included, and the aerodynamic drag or CDA. This can be obtained from a coast down test, or alternatively there is a list of cars which can be used as a reference in the help file under Other, General, CDA figures. The rolling resistance is less important, and for most applications can be left as a default 0.022. So for our simple example, the car had 150 kilowatts at the wheels, had a CDA of 0.55 and a total mass of 1450 kilograms. Check in the XY graph that the figures input are realistic by comparing the speeds with the sim speed against distance. Look particularly at the speeds at the apexes to see that they look approximately right, and that the rate of acceleration fits with that of the data. Note that the accuracy of this would increase by adding the power curve, gear ratios, etc., but this simple example is close enough for us to look at the results. The simulation tool is intended to highlight areas for improvement, not simulate absolute lap times to hundredths of a second, and as such it does not take into account gradients, cambers, and weight transfers on a vehicle. So when looking at results, acceleration uphill, off-camber corners, etc. would all be highlighted, so it is important to understand the limitations when looking further at the data. If we look at the fastest lap and colour the track map based on Sim's time slip, we are comparing the selected lap against the simulated lap, with any slower areas coloured in red. We can see the simulation indicates that there are small improvements being made in most of the braking zones. The area of biggest improvement is in the braking zone approaching the hairpin. If we look at the quick graph, we can see that there was more grip available for heavier, later braking. If we look at sim time slip rate in the graph, we can see that the biggest spike for time slip and the loss of time is shown here. We can also use the simulation tool to examine vehicle modifications before they are done. Would money be better spent on slick tyres, engine modifications, aerodynamics, gear ratios? In this example, a small increase in power estimates a 3/4 of a second improvement per lap.